All right, folks, this is it for 6.2, just 6.2a and b, but this one might be a little bit long, so I apologize ahead of time. So we're solving separable differential equations here, just more practice with that. We're going to look at exponential growth, which we already looked at a little bit, but we're going to look at a slightly different example here. And then we're going to look at something called logistic growth, which we will actually come back to later on in the year to talk more about when we learn some more integration techniques. So how do we know when a differential equation is separable and when it is not? So the ones we've looked at so far have all been separable. All right. If we can write them as all the y guys, everything that has a y on one side with the dy dx, and everything that has an x on the other side, and we'll say m of x here is what we're calling it, then it is separable. We can separate it. All right. And then we can just, from here, we can just integrate each side. All right. So if we can move everything with the x's over here and everything with the y's over here, like if we move the y over, we'd have 1 over y times dy dx equals x divided by x squared plus 2. This is a separable equation. So we can just integrate each side, right? What I kind of like to do is just say, I move the dx over here, and then I'm like, oh, I'm integrating this side with respect to dy and this side with respect to dx. That's actually kind of what's happening, but you're not really multiplying the dx over. It's kind of not right to say that, but I do it anyway. All right, so over here we get the ln, the absolute value of y. Over here we do some substitution. U would be x squared plus 2. Du would be 2x dx. So we need a 2 and a 1/2 out front. So we'd have 1/2 the integral of du over u. So we'd get 1/2 the ln of the absolute value of u. And then we go back to, actually plus c, I guess. And then we go back and we have 1/2 the ln, the absolute value of x squared plus 2 plus c. We'd notice that this is always positive, so we don't really need the absolute value there. We could bring in the 1/2 as an exponent, and we get the ln of the absolute value of y equals the ln of the square root of x squared plus 2 plus c. And now we can raise both sides to the e, and we get y equals here that cancel out, but we really just want to say e to this whole thing first. And now we separate it, e to the ln part times e to the c, and this is just another constant, we'll say c1, and here the e and the ln cancel out. So what we get is c1 times the square root of x squared plus 2. So we get our answer for that guy is y equals some constant times the square root of x squared plus 2. All right, so that was a little tricky, but hopefully something we can do. Let's try the next one here. Find the equation of the curve that passes through the point 1, 3 and has a slope of y over x squared at any given point. So if it has the slope of that, and it looks like it means our variables are x and y, that means dy dx is equal to y over x squared. And we can just divide both sides by y to bring the y over. We get 1 over y with the dy, and we'll get 1 over x squared with the dx. And now we can just integrate each one. This is going to be the ln of the absolute value of y. This would be, let's say, the integral of x to the negative 2 dx, which is going to give us x to the negative 1 over negative 1, or negative 1 over x plus c. All right, we can take the e of both sides, or we can plug in the point now. It's really up to you. If you plug in the point now, then you got to move the c around and actually move the c around. If you wait to the end, that's fine. You can wait to the end. If we take the e of both sides, we get y equals e to the negative 1 over x times e to the c. Maybe we'll call this c1. And then we can say e, if we have c times e to the negative 1 over x like that. And now we can plug in the point. So we get 3 equals c e to the negative 1 over 1. So we can say that this is c e to the negative 1, or c over e. Multiply up the e, and we get c equals 3e. So our final story, our final solution, our particular solution would be 3e times e to the negative 1 over x. And there's some neat things we can do here. So this is e to the first times e to that. We can say this is 3e to the 1 minus 1 over x. That works. Or we can leave it like that. It's just a matter of trying to dress up a pig at this point, try and make it look pretty. All right, here's another example. Let's pick another color here. We'll go with the dark red. So we've got y of 0 equals 1. Find the particular solution to all this. Oh gosh. So look, here's our y prime here. So we want everything with x on the other side. So I'm going to just go ahead and subtract this guy over to here. So we'll get negative e to the negative x squared, y squared minus 1 times y prime equals negative xy. And now I'm going to divide this guy on both sides. Like that. So we'll get y squared minus 1 times y prime equals, okay, these negatives are going to cancel out. I can actually bring this guy up to the top and just change that to positive. So we'll have y times x times e to the x squared, like that. Now I can just divide by y. And there we go. So now we can just take the integral of this side of y squared minus 1 over y with respect to y. And that'll be equal to the integral of that side, x times e to the x squared with respect to x. So over here, remember, if we have one guy on the bottom, we separate. That'll be y minus 1 over y dy, the integral of that. Over here, we're going to do substitution. We'll say u equals x squared, du equals 2x dx. So we get a 2 here and 1/2 there. So we get 1/2 the integral of e to the u du. So we get 1/2 e to the u, which is just x squared. Throw my c over there. Over here, we're getting, let's see, that's going to be y squared over 2 minus the ln of the absolute value of y. And it's going to equal this 1/2 e to the x squared plus c. And it tells me, I'm not going to try and solve for y here. This would be a mess to try and solve with y, with this y squared and the ln of y. But it tells me if I plug in 0 for x, I get 1 for y. So I can plug in 1 everywhere there's a y, and a 0 everywhere there's an x, and we should be able to solve this for c. Oops, 1. All right, so ln of 1 is 0. 1 squared is 1. 1 over 2 is 1/2. So we get 1/2 equals 1/2. E to the 0 is 1. All right, so we'll get 1/2 plus c. So if I subtract the 1/2 from both sides, I'm going to get c equals 0. So I end up getting y squared over 2 minus the natural log of the absolute value of y equals 1/2 e to the x squared as my particular solution. I don't have any c's anymore. So there we go. All right, another application with exponential growth. So the rate of change of the number of coyotes, n of t, so that means the rate of change would be n prime of t, where n of t is the number of coyotes, in a population is directly proportional, so is equal to a constant times this, 650 minus n of t. So now we have an extra number in here. We didn't have that last time we did these sort of problems, where t is the time in years. When t equals 0, we have 300. So we got 0, 300. When t equals 2, the population is increased to 500. Ooh, busy coyotes. And the population, find the population when t equals 3. So n of 3 equals what is what we want to know. All right, so, well, I don't even need to write this as n of t. Let's write this as dn dt equals k times 650 minus n, like that. And then I got all the n's need to be on this side over here, and all the t's will move over there. I'm just going to leave the k, so we get dn over 650 minus n equals k dt. Integrate both sides. Going to have to do a little substitution over here, because the bottom was not just n. So we get negative dn. So we get a negative here and a negative here. All right, so there's the du over u. So this is negative ln of the absolute value of 650 minus n. Over here, we're just going to get kt plus c. Call that c1. All right, we can move the negative over. So we'll get the ln of 650 minus n equals negative kt minus c1. Doesn't really make much of a difference if we call it plus or minus. All right, we take the e of both sides. So we get 650 minus n equals, we'll call this other c, maybe, I'll just call it c2, sure. E to the negative kt. And subtract the 650. And then change all the signs. We'll just call this another c. Like that. All right, so now we've got n as a function of t, right there. Now we need to find, well, c and k. So if we plug in 0, 300 will equal c e to the 0 plus 650. So basically we get 300 minus 650 equals c. So that's negative, what, 250? So there's what c is, negative 250. And now if we plug in the other point, we get 500 equals negative 250 e to the negative k times 2 plus 650. So if we subtract 650, we get negative 150. Divide by the negative 250 is e to the negative k times 2, or negative 2k, I guess we say. Negatives are going to cancel. 150 over 250 is 3/5, so 0.6. Take the natural log of both sides. Divide by negative 2, and that's k. So k is the negative ln of 0.6 over 2. All right, so now I've got this final function, n of t is negative 250 e to the negative ln of 0.6 over 2 times t plus 650. All right, and again, if I had a calculator, I can change these all to decimals if I wanted to, but I'm just going to leave it like that for now. And now I want to know n of 3, so I'm just going to plug in 3. So we get negative 250 e to the negative ln 0.6 over 2 times 3 plus the 650. And whatever that works out to. Looks like it's going up, so it's probably getting closer and closer to this 650 here. All right, last one, logistic growth. So everything we've been doing has been exponential growth. It's been like e raised to something times t. All right. We can also have something that looks like this. And the equation, if we graph it, ends up looking like this. So it hits some sort of horizontal asymptote at this L value. That is our horizontal asymptote. So this number on top is our y equals L is our horizontal asymptote. All right, then in other words, that's what happens as t goes to infinity, positive infinity. Negative infinity, it looks like it's going to go down to 0. But we don't really go to negative infinity when we're working with time. We start at time t equals 0. All right, and this works whenever we have a differential equation that's of this form. So the rate of change is equal to a constant times how many are there, and basically the total load, which is L, or the carrying capacity as we sometimes call it, minus how many we've got. In other words, this is the space that's left, and this is how many that we have right now. All right, so it's proportional to both. And that's a common thing, because usually there's a carrying capacity. We can't have more than a certain number of wolves. There won't be enough food for them, and so on. So a state game refuge releases 40 elk into a game refuge. After 5 years, the elk population is 104. That's a point. 104. And at the beginning, we had 0, 40. So we have 2 points. The commission believes the environment can support no more than 4,000 elk. There's our L, 4,000. The growth rate of the elk is of the population P is dp dt equals a constant times P times 4,000 minus P, where T is the number of years, right? A model for the elk population in terms of T. So really, we're just plugging into this. So we're going to get that y of T. I guess we're not using y here. We're using P, huh? So P of t, population at time t, is equal to L over, well, L is 4,000, 1 plus CE to the negative KT. Well, we need to solve for C and negative K. Luckily, we've got these 2 points. So if we plug in 0, we should get 40. So we got 4,000 over 1 plus C e to the 0, which is just 1. So we get 4,000 over C plus 1 equals 40. So if we multiply this up and divide the 40 down, we get C plus 1 equals 4,000 over 40, which gives us 100. So if we just subtract the 1, it looks like we get C equals 99. All right, so now we've got C. Now we use the other point to find K. So we know P of 5 is 104. So we got 4,000 over 1 plus, now we plug in the C, we know that, 99 e to the negative K times 5. So negative 5K. And now it's just a matter of solving this. So we multiply this up, divide this down. We get 1 plus, I guess I shouldn't say equals, goes to 1 plus 99 e to the negative 5K equals 4,000 over 104. Subtract 1. Divide by 99. Take the natural log. And divide by, there was a 5 here, wasn't it? Negative 5. All right, so now we need to type all of that in. So let's see, we're dividing by 99 first, then taking the natural log. So the natural log was above all this side here. And let's see, I do have a calculator somewhere. I do want that as a number, so let's turn that on. Move it out of the way here. And we're trying to type in this. So we've got the natural log of, let's see, we got to do the top in parentheses. So 4,000 divided by 104 minus 1, close parentheses. And that's divided by 99. And then close parentheses again. That's closing the natural log. And then we're dividing all that by negative 5. 0.19436. And that's our K. All right, so now the model we've got then is P of t equals 4,000 over 1 plus 99 e, and then we had negative in front of the K, so it's negative 0.19436 t. I'm keeping lots of decimal places because remember this is AP Calc and we need 3 decimal places correct in our answer. Use the model to estimate the elk population in 15 years. All right, so P of 15 would be, according to our model, 4,000 over 1 plus 99 e to the negative 0.19436 times 15, like that. And that's just a matter of just plugging it into the calculator. So let's pull our calculator back and plug that in. So let's see, we've got 4,000 on top, divided by, parentheses, the whole bottom, 1 plus 99, second, e raised to the 15 times negative what we just had up there. Second answer. Oops. Shucks. Let me try that again. 4,000. I just hit the wrong button. I needed to hit that one. Divided by, parentheses, 1 plus 99 e raised to the, I'll put the negative with the 15. Oh, that was an extra 5. Times second answer. There we go. And it's using that number right there exactly. Oh, I don't want my parentheses up there. I want to come down first, and then I want parentheses. There we go, the whole bottom. And we get 628.538. And this is elk is our units here. And then we ask ourselves, does that seem reasonable? Let's see, we had 40 at the start. After 5 years, we're at 104. And after 15 years, we're at 600. So it's not like we're at 1,000,000. 600 still seems like a reasonable number of elk to me. All right. Find the limit as t goes to infinity. All right. Well, we take the limit as t goes to infinity of all this. And let's see what happens. So we've got 4,000 over 1 plus 99 e to the negative 0.19436t. So if infinity goes in here, e to the negative infinity, because this is negative, gives us 0. So we end up getting 4,000 over 1 plus 99 times 0, which is just 4,000, which we knew before was our horizontal asymptote. So we do get y equals 4,000, maybe not y equals, in this case, p equals 4,000 is our horizontal asymptote. In this case, it is 4,000 elk. P. All right. Told you this was going to be a long one. All right, so that's it. Exponential growth, logistic growth, and separable differential equations. This is it for 6.2, so check the Google Classroom for the homework.